Biochemistry. We were in yesterday's lecture talking about the properties of amino acids. So beginning, let us start from where we ended. The properties of amino acid. The other property of amino acid after their amphoteric nature was their optical activity. So amino acids have an optical activity and they have the ability to rotate the plane of polarized light either towards right or towards left. That is why they are being called as optically active, either levorotatory or dextrorotatory. As I told you, the standard structure of an amino acid, alpha amino acid, is being represented by the four groups: COOH group, the hydrogen, the basic group, NH2 group, and the side chain which is present. Because of the presence of these four different atoms, this amino acid is optically active because of the presence of chiral carbon atom. As the four valencies are completely different from each other, so these are said to be optically active. Hence, amino acids are another property of amino acid is amino acids are optically active. Optically active. As they are optically active, they can rotate the plane of polarized light towards the right or towards the left. If they are going to rotate the plane of polarized light towards the right, then it is said to be the dextrorotatory D amino acid. And if they are going to rotate the plane of polarized light towards the left, then it is said to be the levorotatory amino acid. Then what is being done in the experiment is that a light source is being taken. There is a light, and this light has rotations in every direction. There are particles which are moving in every direction, and then this light is being passed through a prism. The prism is referred to as Nicol prism. This is the Nicol prism through which this light is being passed. And when the light is being passed through this Nicol prism, then what happens? When this light is being passed through the Nicol prism, then the light get converted into a plane polarized light. It gets transformed into a plane polarized light. Now this plane polarized light is being passed through a cuvette. This is a cuvette, and in this cuvette a solution of amino acid is being placed. Solution of amino acid is being placed. Once the solution of amino acid is being placed here, then what will happen? This solution of amino acid will turn the polarized light either towards the right or towards the left. That is why that is said to be dextrorotatory and levorotatory in nature. Now, this could also be understood on the basis of the type of groups that are being attached over the amino acid. Except glycine, all other amino acids are optically active. All others are optically active. Glycine is optically inactive because it lacks any chiral carbon atom, because in the case of glycine, what we find is that there are two hydrogens which are present here, making this carbon achiral. And because this is not chiral, that is why it won't be able to rotate the plane of polarized light. Now, optical rotation is being measured in a particular value, and that is referred to as the optical rotation is being represented by alpha. And so the quantitative measure of the optical rotation is referred to as optical activity of the molecule, and the optical activity of the molecule is being represented by a formula. The formula that is being used to represent the optical activity of amino acid is T alpha D, that is optical activity at standard temperature is being represented as T alpha D equals to observed rotation divided by length into concentration. The length is taken to be in decimeter and the concentration is being measured in gram per ml. It is being measured in decimeter and it is being measured in gram per ml. That is concentration. Then observed rotation at a standard temperature is being measured in the form of alpha, which is referred to as the optical rotation of any amino acid. So if we can assume the values of observed rotation, length and concentration, we could determine the specific rotation of an amino acid. The specific rotation of an amino acid at a particular temperature and at a particular light intensity. This is specific rotation. Now, so amino acids are optically active. The third property, the next important point. Each amino acid, whichever we have studied up till now, can be specifically classified through a diagram, through a chart, and that chart we can analyze that which are the different types of functional groups. On the basis of functional group, we can categorize the different types of amino acids. Now how we are going to categorize them out? Now see, we are going to write here amino acids, and now we are going to classify these amino acids into the following different types. That means here we are taking only the standard amino acid. Now what is a standard amino acid? Standard amino acids are those amino acids which are being encoded by the genome and which takes part in protein synthesis. These are the one which takes part in protein synthesis. Takes part in protein biosynthesis. See, more than 300 amino acids have been discovered, but there are only 22 standard alpha amino acids in nature, because these are the amino acids that take part in protein biosynthesis. Other amino acids do not take part in protein biosynthesis. For example, ornithine, citrulline, these are the amino acids which are found in the case of urea cycle, but they never take part in the case of protein synthesis. That is why they are not is included in the standard alpha amino acids. Now standard alpha amino acids can be classified or categorized into the following different types. They could be categorized into the following two different types. One is referred to as polar, another one is referred to as non-polar. A polar molecule is the one in which there is a charge distribution and we get a delta positive and a delta negative charge. We get a delta positive or a delta negative charge, whereas non-polar will not have any charge at all. Now the polar molecules can again be classified into several different types. That means they could be, polar amino acid could be classified into charged and uncharged. Now see, charged amino acid and uncharged amino acid. Now the charged amino acid can be categorized into two different types, the positively charged amino acid and the negatively charged amino acid. When we are talking about positively charged amino acids are the basic amino acids. They are positively charged amino acid. Positively charged, and the other one is said to be negatively charged. Now, negatively charged and positively charged amino acid. Positively charged amino acid include all basic amino acids. And negatively charged amino acids will include all acidic amino acids. Now, basic amino acid include arginine, lysine, represented by R, lysine, represented by K, and histidine, represented by H. Whereas acidic amino acids which are present, the acidic amino acid here include the aspartate and glutamate, ASP, represented by D, aspartate, GLU, glutamate. Whereas the others are said to be the uncharged polar amino acid, while the other one will be referred to as non-polar amino acids. Now, uncharged amino acid. There are amino acids which lacks any charge, but they are present in the structure of the protein. So those are said to be the uncharged amino acid. Now, which would be the uncharged polar amino acid? They would be the one which contains a functional group that could be hydrolyzed or that could assume a structure with a delta negative or a delta positive charge. Now we have to look and now in these that which are these uncharged polar alpha amino acid. For example, the functional group containing amino acid: tyrosine, represented by Y contain an hydroxyl functional group will be included here. Cysteine represented by C contain an SH group will be included here. Methionine M will be included here. Aspartame ASN CONH2 group will be included here. Glutamine will be included here. So there are several different types of functional groups containing amino acids, those which are uncharged but still kept in polar. Now the non-polar amino acids could be still categorized into the following two different types. They could be categorized into the aromatic and the aliphatic, unpolar or non-polar amino acids. Now they could be classified into aliphatic and aromatic. Aliphatic. Now, which are the aliphatic? The glycine, alanine, valine, glycine, alanine, valine, leucine, isoleucine, proline. They are all aliphatic in nature. Now when you are talking about aromatic, then in the case of aromatic, these are the one which contain an aromatic ring. The aromatic ring is present in the case of tryptophan, tyrosine. Now see, here I am not going to include tyrosine because it is although aromatic, but it is an uncharged polar amino acid, not a non-polar amino acid. I am just writing it here for the significance that you can remember it, that it is aromatic in nature. Now tyrosine, and the third one is referred to as your phenylalanine, PHE, represented by F. So these are the different amino acids. Other amino acids, if any, would be included in the uncharged amino acid. So let us just count the number of amino acids. Now we have other different amino acids. As I told you, there are two other distinct amino acids which have also been included. One is referred to as the selenocysteine, another one is referred to as the pyrolysine. Now where are selenocysteine and pyrolysine present? Selenocysteine is the 21st standard amino acid which is being encoded by a stop codon. Now note, there are two other amino acids which have been included. Firstly, let us count whether these are 20 standard amino acids have been written. Glycine, alanine, valine, leucine, isoleucine, proline, methionine. Where is methionine? Methionine, cysteine, threonine. Now threonine is also a polar and uncharged amino acid because threonine also contains a hydroxyl group. Serine is also a hydroxyl group containing amino acid. It also contains a hydroxyl group. So now the number of amino acids that we have written: 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13, 14, 15, 16, 17, 18, 19 and 20. We have classified all the 20 different standard amino acids. Now there are two other amino acids which have been included. These two amino acids, which are the two other important amino acids that have been included? It was only in the year 2001 that selenocysteine was being represented. Selenocysteine represented by a triple letter codon that is referred to as SEL. This selenocysteine is the 21st standard amino acid to be discovered, and it is being encoded by a codon that is referred to as the stop codon. Selenocysteine, represented by the single letter O, is the 21st standard amino acid encoded by stop codon. Now, which is the stop codon that encodes for selenocysteine? It is UGA, opal. Now, there is another 22nd standard amino acid which have been included. The 22nd standard amino acid is referred to as pyrolysine, PYR, represented by U. This pyrolysine is the 22nd standard amino acid. Now, I am writing it here. The selenocysteine was being encoded by UGA stop codon, and pyrolysine is being encoded by UAG stop codon. Now, what do you mean by a standard amino acid? As I have already defined, takes part in the protein biosynthesis. They directly takes part in the protein biosynthesis. They are not being interconverted from one form to another. Certain teachers confuses the hydroxyproline and hydroxylysine with a standard amino acid. No, they are not at all an standard amino acid. Hydroxyproline and hydroxylysine are being produced after a post-translational modification. That means translation is over, then the modification takes place. Then such type of amino acids which are being produced are non-standard amino acids in nature. So we have classified the different types of amino acid here. Now what we have to understand is that there are certain questions which are being asked from the weight of the protein. How to determine the weight of the protein? Now, determining the weight of a particular protein. To determine the weight of a particular protein, there are certain standard assumptions that are being considered. Now, which are those standard assumptions which are being considered? Now, the proteins can be of two different types. It could be a linear protein or it could be a circular protein. But before that, we must have certain assumptions. The weight of an amino acid or a weight of a standard amino acid is considered to be equivalent to 128 Dalton. And while the amino acid is present in the structure of a protein, then there is a loss of water molecule because of the formation of the peptide bond. So weight of an amino acid residue will be equal to 110 Dalton. Now, you must also remember the weight of a glycine residue. The weight of a glycine residue equals to 75 Dalton. So, as well as the weight of a TRP residue, tryptophan residue, is equals to 204 Dalton. Now, the proteins, calculating the weight of a standard protein. Our questions could be asked in the section B from here or in certain other entrance examinations such as ICMR and GATE. Calculating the weight of a protein. How we can calculate the weight of a protein? We can calculate the weight of a protein by calculating the number of amino acids which are present. Supposingly this protein is present, the protein can be either linear or circular. Linear or it is circular with n number of amino acids. Linear with n amino acids or circular with n amino acids. Then they could be calculated by using a standard formula. That means in the case of linear, it could be 118 into n. Now, if a protein is having n number of amino acids, it will have n minus number of peptide bonds. Supposingly there are 10 amino acids. There are 10 students who are standing here and they are just joining their hands together with each other. Then you will find among those 10 students who are standing in linear position, they will have 9 handshakes. That means there are 9 peptide bonds which are produced. So here you can find 118 into n, the weight of one student, minus the weight of the water molecule that is being left. That means 18 into n minus 1. While solving this equation, what you get is that this is equal to 110 n plus 18. This formula could also be derived. Now let us assume when you are talking about linear number of amino acid and there are n number of amino acid, let the weight of every amino acid will be that of 110 Dalton. So the complete weight of amino acid chain would be 110 into n plus an amino acid plus a water molecule weight that would be produced, that would be added, that won't be released if it is present in the form of a linear molecule. If it would be circular, then the last water molecule will also be released. So in the same case, if it is circular, then what you are going to get is 110 into n. So the weight of a protein could be calculated like this directly: 110 into n plus 18. If it is linear, if it is circular, it is 110 into n. So here we can calculate the weight of weight of a protein. The weight of a protein is specifically important when you have to separate the different proteins through size exclusion chromatography. Note, the weight of a protein helps in their separation through size exclusion chromatography. They could be effectively separated through size exclusion chromatography from each other. Now, but when you are taking the weight of glycine residue, if that would be of weight of n glycine residue, in case of glycine and tryptophan, the weights would be 175. You can put the 75 value here, 75 minus 18 value here. So you have to subtract 18 from here. That means it would be 57 Dalton for an glycine residue. And in the case of tryptophan, again you have to subtract 18. So 186 Dalton in the case of a TRP residue. So you can take these values and utilize the same formulas for calculating the weight of an amino acid residues chain in the form of a circular protein or the linear protein while solving your questions. You can solve your questions. If there are queries, you can just comment on us or send to us on WhatsApp and we will be answering back to you. Now, the other properties of amino acid, or while studying the amino acids, firstly we must know about the structure and certain specific properties of a particular amino acid. So now I'm going to talk to you about each and every amino acid in a very specific manner. So let us talk firstly about the most simplest of all amino acids, and that is referred to as the glycine. Now, when we are talking about glycine molecule, there are certain specific properties. Glycine, as you can find, G. This glycine molecule is the simplest of all amino acid, most conserved, the lightest among all, so have a weight of 75 Dalton only, and this didn't have any side chain. That is why this is not optically active. You can look at the structure also. COOH is there, hydrogen is there, and then you have a methyl group. So this is not optically active. As glycine contains very less side chain, or there is almost no side chain which is present in the glycine whatsoever. So we can rotate it in any direction and there would be no steric hindrance. That is why glycine occupies all four quadrants of the Ramachandran plot. It occupies all four quadrants of our plot. Now what is this R plot? I would be explaining it to you. The other amino acid after glycine, the first one, the most simplest, is alanine. The first and simplest of all amino acid that contains a chiral carbon atom is referred to as alanine, as indicated by its structure. You can find here that this is CH3 and there would be, this is NH2 and this is the side chain CH3. Sorry, here it would be NH2. And this is the side chain. So it is the simplest, but it is optically active. Now, as I have already told you, the D and the L amino acid, all the amino acids which are found in the case of eukaryotes are all levorotatory amino acids. They are all L amino acids. So this is L-glycine. This is L-glycine. This is L-alanine. Whereas majority of the amino acids which are being associated with microbes are the D amino acid. They are dextrorotatory in eukaryote. In us, the amino acids which are found are levorotatory. Then after alanine, the next structure or the next amino acid is valine. Now valine could be importantly remembered by the V-shaped structure of the side chain that it has. So if you are talking about L-valine, then you get a structure that is COOH, H, NH2 and this particular structure. Note the characteristic V-shaped structure that is being produced. This V-shaped structure indicates the structure of valine. So whenever you are talking about valine, you are talking about a V-shaped structure that is being produced. So this is the V-shaped structure that is being produced. Now after valine, the next important amino acid is leucine. Now when you are talking about leucine, then in the case of leucine, then you find that there is an increase in the number of carbon atom. Leucine represented by L, and you will find that there is COOH group, there is hydrogen, there is NH2 group, there is an increase in the number of carbon atom. See this. You have added a particular carbon atom. When you have added a particular carbon atom, then you have framed the structure of another amino acid, that is that of leucine in nature. Now after leucine, you find that there is another amino acid that is referred to as isoleucine. Isoleucine is being represented by ILE, isoleucine. Now isoleucine has the structure COOH, H, NH2. See, this is isoleucine, so there would be a carbon atom that would be moving from here to here. See, this carbon atom has moved from the gamma carbon atom to the beta carbon atom and is present at the beta carbon atom. That is why it is referred to as isoleucine in nature. Now when we are talking about isoleucine, then isoleucine, as we can remember, it is one of the most hydrophobic amino acid in nature. So isoleucine is most hydrophobic. Most hydrophobic amino acid. So this, when present in the case of globular protein, is deeply suited, and when it is present in the case of fibrous protein, it is superficially suited over the structure of the protein. Proline. Now talking about the structure of proline. Proline is an exception because it has an amino group containing amino acid. Now the structure of proline can be remembered from the structure of a temple. You can just visualize proline as a temple over which a flag is being placed. So you can look at the structure of proline. And there is the flag which has been placed over the proline, or you can remember it by the structure of a tent. And of course, if this is a tent, then you have to make a window, and that window is made up of NH. So this is the NH that is present, NH2 positive. So this is the amino group that is present. That is why this structure is referred to as the proline. Proline always disrupts protein structure. Why? Because it introduces a bend within the structure of a protein. If there is a polypeptide, then see, the direction of the polypeptide is being altered by an angle of 90 degree. One polypeptide is going to be attached here, one amino acid is going to be attached here, another here. So it is going to alter the structure or the bonding by an angle of 90 degree. Disrupt protein structure by producing a kink and altering its structure by 90 degrees. So there is 90 degree, the structure has been altered. So glycine, alanine, valine, leucine, isoleucine, proline. Let me just point it out like this. This is glycine, alanine, valine, leucine, isoleucine, proline. Now the next is referred to as the methionine. Now methionine has a structure in which, although the thiol group is present, so methionine, MET, represented by M, this is an amino acid that contains the thiol group. Although it contains a thiol group present within itself, but this amino acid that is present, this amino acid has a thiol group in such a manner that it won't be able to form disulfide linkages with another methionine. So how it is being oriented? COOH, H, NH2, C, S, C. So see this, the sulfahydryl group is present, thiol group is present, or the beta mercapto group is present. Once the sulfahydryl group, the thiol group, or the beta mercapto group is present, then also it can form a disulfide linkages, because there is the sulfahydryl is being sandwiched in between the methyl and the methylene groups which are present. Glycine and valine, leucine, isoleucine, proline, methylene. Now the other amino acids are cysteine. Now cysteine is an amino acid which has a free thiol group. That is why it has been classified into a polar charged uncharged amino acid. We are talking about cysteine now. See this, just rubbing these out. Cysteine, the amino acid, the 8th amino acid, the structure of cysteine. When you are talking about cysteine, then what you find in the case of cysteine is that there is the presence of thiol or mercapto group, mercapto group. But the thiol or mercapto group that is present in the case of cysteine is actually free. When this thiol or mercapto group is free, then this can form disulfide bridges with another cysteine residue. Free SH group tends to form disulfide bridges. That means the two cysteine could link with each other and lead to the formation of homocysteine. So cysteine structure could be like this: COOH, H, NH2, then there is your C, and then there is SH. This is CH2. This is one cysteine, and then there is another cysteine: COOH, NH2, then there is hydrogen, then there is CH2, then there is SH. Now these two cysteine can react together and they will lead to the formation of a structure that is referred to as cysteine. They will lead to the formation of a structure that is referred to as homocysteine. Now you should not get confused with another structure, that is the structure of cysteine. Cysteine is another molecule that has almost the similar structure. It has the structure of COOH, C, H, NH2, C, H2, CH2, and SH. This is cysteine and this is cysteine. This is cysteine. This is cysteine. Now when the two cysteines combine together, then they will lead to the formation of homocysteine. When the two cysteine combine together, they lead to the formation of homocysteine. Now compare this homocysteine, how the homocysteine is being formed. When this thiol group is present, CH2, C, COOH group is present, the hydrogen atoms are there, and the NH2 group. This is homocysteine. Another, in the case of cysteine, this is going to be bound to here. There would be CH2 group, there would be CH2 group, there would be the carbon, there would be the carboxylic group, there would be the NH2 group, there would be the hydrogen group. So this would be referred to as homocysteine. Now, cysteine is the only amino acid that has the ability to form the disulfide linkages in between proteins. Now you should remember the definition of protein that I told you in the L1 lecture. The proteins are linear unbranched polymers of alpha amino acids that I have told you. They are linear, they are unbranched. So if I take a cord, then the structure of the protein would be like this. This is linear and unbranched. When this is linear and unbranched, then how one protein could interact with another protein? Then these two proteins won't be able to interact with each other. Now supposingly this is another protein, then both the proteins are linear. Then what is going to happen? They won't be able to interact with each other in a side-by-side manner. So what happens? The cysteine residue actually interact. One cysteine residue from one protein is going to interact with another cysteine from another protein and is going to form a disulfide linkages. As I always tells you that if you will have the linear endurance polymer of proteins, then what will happen? As you are going to stretch your hands, the proteins must be separated, but they are not being separated. They are still being joined with regard to each other because of the presence of hydrogen bonding, because of the presence of disulfide linkages which are associated with the keratin protein of the skin. So cysteine is responsible for side to side or chain to chain interaction in the case of proteins, making the proteins a tougher structure as compared to any other molecules. Now, after cysteine, the other amino acid is the aromatic amino acids. Which were the aromatic amino acid? Tyrosine, as I told you, represented by Y. Tyrosine, phenylalanine, represented by F, and tryptophan, represented by TRP and W. Now, they could be classified as aromatic because they have a ring system present in between within their structure. Let us see the structure of tyrosine. Tyrosine has the ability to absorb UV radiation similarly to phenylalanine and tryptophan because of the presence of this aromatic ring, NH2. Then there is carbon and there is a ring-shaped structure. This ring-shaped structure is that of tyrosine. It also contains a hydroxyl group. As it contains a hydroxyl group and a ring, so it is this molecule which has the ability to absorb the UV radiation at 279.6 angstrom. Now, the other is phenylalanine. The phenylalanine has the similar structure except that the hydroxy group is absent. So there is the structure carbon and then you will get the ring shaped structure, but there is no hydroxy group. So this molecule has an ability to absorb the UV light at 271 angstrom. And third one, the tryptophan. The tryptophan has a complex structure. This is the heaviest of all, some important point, heaviest of all amino acid. Heaviest of all amino acids. As I've already told you, its weight is 204 Dalton. Secondly, it is being encoded by only a single codon, so it is the least abundant of all amino acids. Least abundant. As it is least abundant, so it is present at a precisely very low concentration within the structure of the proteins. It is present only at a concentration of 1.2% within the structure of proteins. 1.2%, because it is being encoded by only a single codon. A single codon encodes it. No, the single codon is UGG. Tryptophan, when you look at the structure of the tryptophan, what you find is that this has a carboxyl group, the standard amino acid structure. Then you find that there are rings which are present, and those rings forms a complex network of structures that constitute the structure of tryptophan. They could be effectively remembered by using a trick CCHNH. CCHNH, and then making a ring-shaped structure. When you make a ring-shaped structure, this is the structure that you would be getting. So you would be getting two different rings combined together in the structure of the tryptophan. Oh, sorry. What you find is that here is the NH group, NH. There is the ring-shaped structure. Because of the presence of this particular ring, the tryptophan is also going to absorb the UV radiation, and it absorbs the UV radiation at around 281 angstrom. The values may vary from one author to another, as they are highly controversial in one points to another. With different books, they can effectively vary from one to other. So after tryptophan, there are other amino acids. You can remember the structures by using this trick only. The other amino acids that are basic and the acidic amino acid. When we are talking about the basic amino acids, There are three basic amino acids: arginine, lysine and histidine. Arginine, the 10th arginine, lysine and histidine. In the case of arginine, what you find is that the side chain which is present has a specialized group, and that group is referred to as guanidino group. Alpha, beta, gamma, delta, epsilon. Now see, this group, each and every basic amino acid, when you're talking about arginine and lysine, they will have the gamma carbon atom, they will have the epsilon carbon atom present within themselves. This is alpha, this is beta, this is gamma, this is delta, this is epsilon carbon atom, and this group, this complex structure, this group is commonly called as guanidino group. This is called as guanidino group. Guanidino group. This is commonly called as the guanidino group. This arginine is the structure, as you can see that it has the formula NH2CONH2. So this would be the molecule where you're going to accumulate the ammonium ions or the waste product of the body, the nitrogenous waste, and you're going to release it out in the case of urea cycle. Then there is the lysine. In the structure of lysine, what you can find is that represented by R, represented by K. In the structure of lysine, what you are going to find it out is that there is an epsilon amino group that is present. COOH, H, NH2, beta, alpha, beta, gamma, delta, epsilon naught, and there is the NH2 group, which could be written as NH3 positive or could be written as NH2. So what you are going to find it out is that there are large number of rotatable bonds. So the largest number of rotatable bonds which are present in an amino acid is lysine. Now the next is that of histidine. Arginine is the only amino acid that has an isoelectric point.
We have one problem. This is not homocysteine, this is cysteine actually, sir.
Cysteine, and this is homocysteine.
This is again
this is cysteine and this is cysteine. So we are live again because of a technical fault. We have to just move to offline mode. Now please, there are certain of your queries that I would be answering after the lecture, and we would be looking at everything. Again, if you have certain queries, keep writing and I would answer you out after the lecture is being finished. Just half an hour more so that we can concentrate on the topic, and after finishing the topic I would be coming back to you. Now when we are talking about histidine, histidine is being represented by H, and it is the only we were talking about arginine. In the case of arginine, arginine is a basic amino acid which has a very high isoelectric point. That means it is basic, that is why it has the highest isoelectric point of 10.6 or 10.7. 10.6 isoelectric point represented by Pi. Now histidine, it is basic in nature, and this histidine which is present, it has an isoelectric point close to physiological pH, as it has an isoelectric point close to physiological pH, that is close to neutral pH 6.8 approx. So it is being found extensively in the active site of the enzymes. This is being found extensively in the active site of the enzymes. Found extensively in the active site of the enzymes. Its structure could be effectively remembered after inverting the structure of the tryptophan, you have seen that the structure of the tryptophan was having CCHNH, of course, because there is C, there is a double bond there present. Now this structure would be CCHNH. Instead of CCHNH, it would be CNHCH. CNHCH would be present within the structure of histidine. So let us look at the structure of histidine. What we find in the case of a structure of histidine is that C, COOH, H, NH2, there would be CH2, C, NH, there would be the CH, there would be a carbon atom, and such type of ring shaped structure would be formed. But this is not an aromatic ring. This is not an aromatic ring. There is no aromaticity that whatsoever is being reported here. So there is no aromaticity. As there is no aromaticity, then what is going to happen? This is not going to be aromatic in nature. See this? Now this will have certain double bonds present here. There would be the NH2 molecule, NH molecule, that is CH molecule that is present here. This is the structure of histidine, which is also a basic amino acid. Now the acidic amino acid. The acidic amino acid have been categorized into the following two different categories: the aspartate and glutamate. The aspartate and glutamate we have finished up till 12th. 13th is the aspartate represented by D, glutamate represented by E. Aspartate have a structure COOH, hydrogen, NH2, C, COOH, CH2. Now the aspartate, which is in highly acidic, it is highly acidic, so it has a very low pi of equivalent to 2.6. so it has a very low pi. The pi in the case of aspartate is too low, and it is going to be 2.6 in the case of aspartate molecule. So this is too low. When you are talking about glutamate, the glutamate is similar to aspartate. It also contains the carboxyl group, but it contains two carbon atom instead of a single carbon atom, which is present in the case of aspartate. So in the case of glutamate, what you find here in its structure is that there is the COOH group, there is the NH2 group, there is CH2, CH2, COOH. Glutamate structure. Glutamate. This glutamate contains gamma. The gamma carboxyl group is present in the case of glutamate. That is why this will be referred to as the gamma carboxyl group containing amino acid is glutamate. You have to remember this because this has certain specific importance in other blood clotting, where this group is going to react and form a isopeptide bond. I would be covering that topic when it would come in the particular blood clotting topic. Now, after aspartate and glutamate, there are other molecules. Aspargine, ASN. Aspargine, glutamine. In the case of aspargine, what you find is that there is a group that is present, CONH2. In the case of glutamine, again, there is a group that is CONH2 which is present. So these are the structure of aspargine and glutamine. Then there are other OH containing amino acids such as the serine and the threonine. The serine and the threonine, 12, 13, 14, 15, 16. So this is one was 16. Now serine. When we are talking about serine, it is an hydroxyl group containing amino acid. That is why this could undergo phosphorylation. Any hydroxyl group containing amino acid can undergo phosphorylation and dephosphorylation, and thus these are the amino acids that are found at the active site of the protein, and they are the substrates where the phosphorylation can activate the protein, or the dephosphorylation can inactivate the enzyme or the protein. Now serine based proteases are there, serine based enzymes are there, COOH group is there. There is the NH2 molecule, there is the CH2 molecule, there is an hydroxy group that is present, and this is referred to as the serine molecule that is present. Now after serine, there is another molecule, another hydroxy group containing amino acid. That hydroxy group containing amino acid is referred to as threonine. it also contains a hydroxy group. Tyrosine was also containing a hydroxy group. Now what you have to remember in the case of threonine is that this threonine is exceptional. Threonine always confuses. OH group is never added on the second carbon atom, it is always added on the first carbon atom. Threonine confuse करता है, OH group second पे नहीं पहले कार्बन एटम पे हमेशा लगता है. OH is being added on the first carbon atom, not on the second carbon atom. And this threonine is also subjected to phosphorylation. That is why it could also be activated and deactivated with the help of threonine kinases. The next one was the last hydroxy group containing amino acid was tyrosine. We have already seen tyrosine. Then the other amino acids that are also present here is proline. We have seen glycine, alanine, valine, proline, methionine, cysteine, histidine. We have seen any other amino acid that we have not seen. We have almost seen all the different types of amino acids. The only amino acid that could have been remaining, no, these are all 20 standard alpha amino acids, because we were counting it like 2, that is why we have escaped them. So we have finished all the different 20 standard alpha amino acids. The other the other 21st standard alpha amino acid is referred to as the selenocysteine, whereas the 22nd is referred to as the pyrolysine. So you can remember the structure of all of these different amino acids through these different tricks. That is why I have told you the key important point. Now some of the key other important points were that which was the first amino acid to be discovered. The first amino acid to be discovered was arginine. Arginine was the first amino acid which was firstly being discovered. The leucine is the amino acid which has maximum number of codons which are present. That could be remembered by SRL. Serine, arginine and leucine has the maximum number of 6 number of synonymous codons. So they are quite abundant, whereas tryptophan and methionine, they have single codon, so they are found in less in the structure of proteins. Now about the other amino acid, the selenocysteine. Selenocysteine, as I have already told you, it is the 21st standard amino acid. It is being inserted at the time of protein biosynthesis rather than being produced after the protein synthesis. It is being encoded by a stop codon that is referred to as UGA, and selenocysteine has a selenium atom, which is one of the most abundant atom which is found in the planet Earth, in the earth crust. That selenium is present and it resembles the cysteine in its structure. In the case of cysteine, there was SH group that was present. In the case of selenocysteine, there is Si, selenium molecule that is being produced. But cysteine is being produced after the post-transcriptional modification of the serine tRNA rather than cysteine tRNA. So you must remember that selenocysteine has been produced from the post-transcriptional modification of the cysteine tRNA molecule, which carries the selenocysteine at the site of protein biosynthesis. Now after that, what we have to study is we have to study about how the other property of amino acid. I have already told you that amino acids have the ability to absorb the UV radiation. There are 3 amino acids which have the ability: the tryptophan, tyrosine, phenylalanine. They absorb UV radiation. The absorption of UV radiation by these amino acids is drastically different. The tryptophan absorbs the maximum UV radiation owing to the large number of chains which are present. There are 2 chains which are present and the energy can be largely absorbed. That is why it absorbs around 281 and absorbs the highest. It absorbs approximately 4 times as large as that of tyrosine or that of phenylalanine. So we get an absorption spectrum. The absorption spectra is being obtained. The tryptophan absorbs much more as compared to tyrosine and phenylalanine. There is an absorption spectrum that is being obtained. Tryptophan absorption, then tyrosine, and then your phenylalanine. So TRP will be absorbing more as compared to tyrosine and as compared to phenylalanine F. So these are the absorption spectrum that are being observed. This is referred to as wavelength. This is referred to as absorbance. Now moving forward, we must understand what is a peptide bond and how peptide bond and isopeptide bond differs from each other. So how much is the time? It's 1 hour. Almost it's a 1 hour lecture. So we would be starting about the peptide bond, the isopeptide bond, how the peptide bonds and isopeptide bond differs from each other, and how the proteins are being oriented in their higher structural organization. On Monday we would be continuing our class on Monday. From Monday onwards the class would be a bit more faster, so you have to improve upon your pace so that we can complete the syllabus on time. Okay, thank you, best of luck, and please do share, subscribe and like our channel so that we can get motivated and move forward towards your completion of your entire